Galactic Reflections has uploaded a video very recently in response to a video by some idiot who has found a Wolfie 6020 video with footage from the cockpit through the head-up display showing the horizon clearly below eye level and slightly curved, and another video by Mr. Sensible with video footage from a high altitude balloon showing the horizon visibly curved with no reference for eye level. He's picked two frames, that the M.A.G.E has picked two frames, one out of each video, and said, hey look, the curvature of the horizon line in these two frames is very similar, therefore the Earth isn't curved. My apologies to anyone who now wishes they'd been wearing oven mittens before they watched this, before they heard that, but yeah, that seems to be what he was asserting. Implication is that viewed from different altitudes you would see different amounts of curvature. Well, that does make a certain amount of sense. Viewed from different altitudes with different cameras, with different fields of view, you might see different amounts of curvature. Viewed from different altitudes with the same camera, with the same settings and the same field of view, you would see different curvature. One thing he didn't take into account in his waffling was that neither of them actually necessarily showed Earth's surface. The Wolfie footage was just a black silhouette of Earth against a sky that was backlit by the sun, and the Mr. Sensible footage had clouds in it. So of course altitude above the ground and altitude above the apparent horizon aren't the same thing, as the clouds would form the horizon, and there may have been clouds in Wolfie's footage, and certainly he didn't provide. I don't think either of the Mr. Sensible may have provided the weather forecast, or META weather forecast for aviators in the area on the day, saying approximately what heights the clouds were at, but those only give cloud base, not cloud tops in most cases, and certainly the M.A.G.E didn't copy that information. Where we are right now is airliner altitude, 11 kilometers. We're not quite up to Wolfie yet, and I'm going to interrupt. Give you a listing and explain what this thing does. Mode 0 is black and white, 640 by 256 resolution. Lots of memory available for things that aren't the screen. Bear in mind this is emulating a computer that had 32 kilobytes of 8-bit RAM to do everything. R% radius of the planet, apparent radius of the planet. It does depend on refraction. For high altitude it should probably be pretty similar to 6371000 because most of the refraction happens at very low altitudes. I've just put in 7 million, you can put in 6 million, 6.5 million, 7 million, whatever you feel like in there. You'll get results probably something like this, unless you put in a ridiculously small or a ridiculously huge radius. You know, if you put in a radius of 1 kilometer or of 1 terameter, you're going to get silly results. GCOL 0,1, unnecessary, it just says draw in white. Altitude is 0. Meaning standing in the sea wearing weighted belt and boots and a snorkel and mask with the water level at eye level on your mask. To 100,000, the Kármán line, the official edge of space. Not that there is a perceptible difference between the atmosphere at 99,999 meters and the atmosphere at 100,001 meters. Step 1,000, so it's going up 1,000 meters at a time, which is kind of slow for that range. Clear screen. Print altitude, print don't leave a space, print the string altitude : space, end of string, don't leave a big gap, %, the actual altitude, don't leave a gap, and then this string, which is just a little m, so it will say altitude : space, then your altitude, and then little m for meters. As you can see up here in the top left, altitude : space, 11,000, little m for meters. Drop equals, this is how far below eye level the horizon is. In meters, parallel to the direction that is down where you are, where the observer is. R% radius of the Earth, plus alt%, meaning how far from the centre of the Earth the observer is, minus r% times r% over the sum of r% and l%. This r% is the radius from the centre to the horizon. This r% is the radius from the centre to the horizon. It's the same radius. Dividing that by the sum of the radius plus your altitude, the distance from the centre to the observer, gives you the ratio of the adjacent and hypotenuse sides of a right-angled triangle with a very small angle down there at the centre of the Earth. Multiplying that by r% tells you how far in the direction that is up where you are from a plane that is level where you are and passes through the centre of the Earth, a point on the horizon is. What a horrible description. But if you subtract that from how far from the centre of the Earth you are, in a direction that is quite obviously up where you are, you get how far below you the horizon is, which is approximately twice your altitude for small values of altitude. That is, small values of altitude relative to the radius of the Earth. The higher you get, the more difference there is, and it tends towards the radius. HR, horizon radius. This is the radius of the flat circle centred drop below your eyes, as in approximately your altitude below sea level, below you, if you're at low altitude, is the radius of the Earth times the sine of the angle whose cosine is that. This is just using cosine and sine to figure out x and y coordinates for the horizon in front of you. For y% is 1 to 4, this is just 4 different values of y%. 1, 2, 3, and 4. Z% is y%. Percent, by the way, it just means this is an integer and uses less memory to keep track of an integer than it would to keep track of a float like drop and HR and A. Z% is y% times 200 plus 200. So it is going to be 400, 600, 800, 1000. Bear in mind the bottom of the screen is 0, the top of the screen is 1024. The plus 200 is so that it doesn't disappear off the bottom too soon. FOV, field of view, is rad, the radian equivalent of y% times 30. So as y% goes from 1 to 4, this is going to go 30, 60, 90, and 120 degrees. But this programming language works in radians, so this converts it to radians. The scalar is 1280 divided by field of view. So the full width of the screen in pixels divided by the field of view gives me a number by which I can multiply an angle in radians to get a coordinate in pixels. Move, minus 640, which is way off the left. 512. I'm just moving level with the middle of the screen and way off to the left, so when I draw a line, it's not going to draw it from some silly place on the screen and make an ugly straight line. And then for A equals minus field of view over 2, half a field of view left of centre, to field of view over 2, half a field of view right of centre, step, field of view over 640, 2 pixels at a time, from the left of the screen to the right of the screen. Draw, middle of the screen plus scalar times A, so it's starting at negative half a field of view, it's going to start at the left edge of the screen, finish at the right. Z%, which is this coordinate 400, 600, 800, 1000, minus scalar times the angle, because we want, scalar is a thing you multiply by an angle in radians, the angle whose tangent is the drop, how far below eye level the horizon is, divided by the radius of the horizon times the cosine of that angle. This is how far in front of you, in the direction you're facing, the horizon, that angle right of the centre of your field of view, so when it starts negative number, it's going to be left of the centre of your field of view, is. The tangent of that angle is how far below eye level as an angle, the angle whose tangent is that ratio, got that the wrong way around, is the angle below eye level of the horizon that far right of the centre of your field of view, whatever it may be, 30, 60, 90 or 120 degrees. Multiplying that by the scalar tells you how far below the eye level line across the screen that I'm not bothering to draw the horizon is. Next angle, so it's cycling through that. Next y%, so it cycles through the positions on the screen and the fields of view. T equals time, repeat until time is greater than t plus 50, waits half a second. Next alt percent, go 1 kilometre higher up and repeat the whole process. So at 0 metres, standing in the sea, weighted boots and belt, mask and snorkel, with the seawater actually across the middle of your mask, the horizon you see is completely flat. And, you know, it's about 5 inches wide, because that's how wide your mask is. And it doesn't matter what your field of view is. So that is all going to be straight lines. We would be here a long time if I didn't do this. There's a speed menu that lets you make it run at twice, 5 times, 50 times, or 100 times normal speed. So here we go, 1 kilometre up with a narrow field of view, still looks flat, but with 90 or 120 degrees perceptible curvature. And that half-second pause is doing absolutely nothing. 2 kilometres up, you're already too high up to be in Britain. Definitely visible curvature. 3 kilometres, serious mountain. The wider your field of view, the more curvature you see. 4 kilometres, we're talking tops of the Austrian Alps here. Curvature even in a 30-degree field of view, but it's much more obvious in a 120. Why it went flat at 5 kilometres, I don't know. That's a weird glitch. Maybe it's just a rounding error. After all, this is only a 640 by 256 resolution screen. 7 kilometres, we're now at the top of Kilimanjaro. Too high to be in Europe. 8 kilometres, high up in the Himalaya. Is Kilimanjaro 5,000 and some? Anyway, this is Himalayan altitude. Definite curvature in the wide angle. And here we are back at airliner cruising altitudes. Wider your field of view, the more curvature you get. Now, Wolfie's video was at 46,000 feet, which I haven't checked, but I think that's about 13 kilometres, and here we are at 13 kilometres. Maybe it's more like 14. Not sure. It's somewhere in this range, so screenshot that, and then let this one fill. And screenshot that. And see whether any of the lines on either of those screens matches Wolfie's video. Of course, depending on the weather conditions when he made that video, apparent radius may have been a bit bigger than 7 million or whatever I put in. Next question is, do any of these curves that we're now seeing from above any altitude at which Wolfie operates, as far as I know, look anything like any of the curves we saw earlier from altitudes way below airliner altitude? Is that 30-degree line, or is this 30-degree line anything like the 90-degree field of view line we saw from 4 kilometres altitude? Perhaps. Or is this 60-degree line that it's drawing now anything like the 120-degree field of view line from 3 kilometres or 6 kilometres? Because if it is, then what this program is doing is predicting that geometrically, without taking refraction into account, apart from the fact that I gave it a slightly large value of 0.5%, the horizon, as viewed with various fields of view from various altitudes, can in fact have the same apparent curvature across the field of view from 2 different altitudes if you have 2 different fields of view. And if that is what this program is showing, then finding two videos taken from different altitudes which show very similar amounts of curvature across the field of view doesn't debunk the globe at all, does it? Here's M.A.G.E altitude. Take a screenshot of that and see whether any of those lines matches the M.A.G.E footage. Or take screenshots of the earlier altitudes and see whether they match parts of the M.A.G.E footage before it popped. Obviously before it popped, but you know what I mean. Further before it popped, at slightly lower altitudes. And for fun, let's modify this to be ISS view. Well, there was no point in doing the 30-degree field of view because it's zoomed in on how far below eye level the horizon is to such a great extent that the 30-degree field of view is off the bottom of the screen. I did make a change to try to correct that, but I didn't correct it by enough. Times speed. There's your 60 degrees. There's your 90. There's your 120. There's another 30 you won't see. These should look right if you hold an old analog clock or watch up with the centre under your eye, which is difficult to do unless you cut half of it off, and the 11 and the 1 lined up with the edges of the screen for 30 degrees. That's not true at all. For the 60 degrees line, you want the 11 and the 1 lined up with the edges of the screen. You kind of use the 11 and the 2 for the 90-degree line, and use 10 and 2 for the 120-degree line, which might require you to get your eye very close to the screen. But if you do that, it should look like you're looking over a ball. Actually, no, it shouldn't, because this is doing the actual angle, not the tangent of the angle, and if you're that close to the screen, that'll cause distortion. My bad.